So in this lesson, we're going to be talking about electromagnetic energy. Yesterday, just to review, we talked about the three types of energy transfer: conduction, convection, and radiation. And radiation is the big one because it's that these objects in space are radiating their electromagnetic energy, and we have learned how to use that, to interpret it, to determine what type of composition, mass, and so on of these different distant objects. So we wanted to spend time talking about this and the electromagnetic spectrum. Electromagnetic waves have electric and magnetic fields with them. That's there for the electromagnetic part. And you can see an example of this picture here. You can see the electric and the magnetic fields together. They transfer by radiation, and electromagnetic waves can either need a medium or matter to move through, or they can move across empty space, which is how the sun's energy is radiated through. That is a vacuum of space, there's nothing. However, things can radiate through air and other types of matter. These electromagnetic waves exhibit what's called a transverse wave property. Here's an example of them, one. Here's a great example, or just a review of the different parts of a wave. Is number one, this is the wavelength from the top of one crest to the top of the next over here is a wavelength. Amplitude is called the height of a wave, and we won't be talking about it now, but we will be talking about it later when we talk about the height of the S waves. They can be used to determine the magnitude of an earthquake. And the crest is the very top of the wave, whereas the trough here, number 4, is at the bottom of the wave. So if you hear this in the future, crest at the top, trough at the bottom. And we will be talking about wavelength a lot with electromagnetic energy. Since now we know what a wavelength is, so here would be one wavelength, we can talk about frequency. We can talk about how many of those waves pass a given point within a second. And that is the frequency. We're going to be talking about the frequency of the gamma rays versus the radio waves. And when we talk about that, that's what we'll be describing. And one wave per cycle is called a hertz. I'm not sure if people have heard that before, but that's what a hertz is. And a wave with 2 cycles that pass a point in 1 second, they would have a frequency of 2 hertz. So just an example here. Here's an example of something that would have a high frequency. If this represented 1 second, you can see there's 1, 2, 3, 4, 5, 6 waves, because if you took this one here with this over here, so there's 6 waves, so that would have a frequency of 6 hertz. Here, this is a low frequency. Not as many waves pass a certain point. And in here, there's 2 complete waves, so this would have 2 hertz. So high frequency, low frequency. So let's test yourself. Which one has the higher frequency? If each of these represents 1 second, which of these would show waves with high frequency? And so if you were to take a very close look at them, check out the waves and see. You can look at the wavelength to help you and see which one has the higher. Stop the video and circle your answer. So hopefully you would see that this has the higher frequency. And it's kind of matched up to the colors on the visible light and the electromagnetic spectrum that we're going to be talking about soon. But this has a higher frequency. You would also look at the shorter wavelength. You're going to get more of those per unit of time. So wavelength and energy. So if a wave has, it says moving from long to short wavelengths. So if you have waves with short wavelengths, they are going to have a higher frequency and therefore more energy associated with them. And so here's an example of 2 people with their ropes. If you thought about it, if you wanted to have less energy, you just kind of gently move the rope up and down, and you would see this wavelength much larger, less frequency. But here, if you wanted to make a lot of waves with the rope between 2 people, you'd have to put a lot more energy into it. And you want to remember that for when we talk about the electromagnetic spectrum. The smaller the wavelength, the more energy associated with it. So the electromagnetic spectrum is a model of the energy that the sun gives off, and the electromagnetic spectrum is arranged by wavelength. This is also on page 14 of your reference table. This is an example. This shows you all of the electromagnetic radiation, starting with gamma over here on the left, X-rays, ultraviolet, all the way down to radio. Here, notice it says decreasing wavelength. So if you were to be asked a question, which of these has the smallest wavelength, you would say gamma has the smallest wavelength. And which has the longest wavelength, you would come all the way over to this side of your chart, and you would say radio waves have the longest wavelength. But you can't forget the visible light that's in here. Often I might ask you, out of the visible light spectrum, which one has the longest wavelength? You would say red. And if I asked you which of the visible light has the shortest wavelength, you would say violet. So sometimes you have to read carefully in questions. It might say visible light, or maybe it's looking at the whole entire spectrum. So now what you're going to be doing is I'm going to be showing you a short video on each part of the electromagnetic spectrum, an overview, and you'll hear the words energy, wavelength, and so on, to review what we just were talking about.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, Scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.